Listeners, welcome to this in-depth walkthrough of one of the most important aspects of automotive engineering, and that is engine assembly of an auto rickshaw, which is a key mode of transportation, especially popular in South Asian countries like India, Pakistan, Bangladesh, and other countries like Italy. Whether you are an engineer, production manager, planner, associate, or simply someone who is interested in mechanical system, let us together explore different stages of the assembly line production supported by real process sheets, cycle time analysis, and production efficiency. And yes, we shall also examine short-term, medium-term, and long-term capacity expansion strategies. As you can see from this cutoff model, you can see different parts of engine assembly, starting from spark plug to cylinder head, cylinder, clutch control, clutch, contact breaker group, flywheel, magneto, and fan, dyno starter consisting of dynamo plus starter motor, number 9 gear group, number 10 differential unit, number 11 reverse gear unit. What we mean by dyno starter, when you turn the ignition key or press the start button of an auto rickshaw, the dyno starter acts like a starter motor, turning the engine over to start it. Our discussion will be focused on establishment of low investment, low capacity auto rickshaw production plant. By low capacity, we mean capacity ranging from 10,000 units to 20,000 units per annum. Under this topic, we shall examine production processes, cycle time, and production capacity of the following shops, and shall recommend action plan to achieve the required production targets. The shops under discussion will be press shop or stamping shop, welding shop, engine assembly, and frame assembly. The process sheets of the engine assembly production line consist of 9 workstations. That is, number 1, washing. We shall be requiring oil bathtub, brush 3 inches. 2 number of workers will be working, and consumable required is kerosene oil. The cycle time is 10.00 minutes. Number 2 workstations. Over here we shall assemble bearings and seals fitting. The total number of parts involved are about 22, and the tools required are nose plier, socket, a small hand press, punches, and spanner and puller for kick spring. Number of workers required is 1, and the estimated cycle time is 10.25 minutes. We are omitting the details regarding number of parts to keep the video brief and concise and to the point. Workstation number 3. Over here we shall be assembling crankshaft and gear assembly. The number of parts to be assembled are 27. We need sockets, spanners, pullers for gear shaft, crankshaft, and push. The consumer required is grease, and the total estimated cycle time is 6.50 minutes. Process number 4. Crankcase fitting. The parts required are 53, required one socket, one worker, and the estimated cycle time is 8 minutes. Workstation number 5. At this workstation, we shall be assembling cylinder, piston, cylinder head, and clutch fitting. The number of parts involved are 28. The tools required are plastic hammer, spanner of different sizes, sockets of different sizes, nose plier inner, fixture for clutch, tool for clutch. The number of workers required is 1, and the total estimated cycle time is 11.50 minutes. Number 6. The parts to be assembled are magnet, HT coil, fan cover fitting, and clutch cover fitting. The total numbers of parts are 80. The tools required are screw and screwdriver, sockets, round file. The number of workers required are 2, and the estimated cycle time is 10.25 minutes. Workstation number 7. At this workstation, differential assembly is to be mounted. Number of parts are 101. Tools required are flights of 2 different types, flat and round, hammers, sockets, circlip plier inner, punch, and special fixture for differential case and cover. Number of workers is 1, and the estimated cycle time is 17 minutes. Workstation number 8. At this workstation, we shall assemble differential, silencer, cooling hood, carburetor fitting. Total number of parts are 28. The tools required are punch for steel, plastic hammer, circular plier inner, spanner, and sockets. The number of workers required are 2. Estimated cycle time is 12 minutes. And the last workstation, number 9, is engine testing. Over here, we need socket, spanner, screwdriver, minus and plus, oil gun, and special tool for plug. 2 workers are employed, and the consumer required are petrol and mobile, and the cycle time is 20 minutes. Overall, the number of parts to be assembled at these 9 workstations are 339. In the current situation, the number of workers are 13, and the total cycle time, which is 104.62, which we shall call as the throughput time. It is about equal to about 105 minutes. In this slide, the process names are listed. The workers associated with all these processes are also listed, and the cycle time, as we have discussed before, is produced here. The total is 13 workers, and the total of the cycle time, which we call as throughput time, is 105.50 minutes. The whole process sheet is shown as a process flow chart from process number one, that is washing, to engine testing, total 9 processes, and after completion, the complete engine is delivered to final or frame assembly line. This is the situation before any improvement. On the basis of same data, let's not compute the current production capacity based on 2 shifts, 40 working hours per shift, and since we are using 2 working shifts, the total available working time is 4,800 minutes. We assume the working efficiency of 80%, and we have listed all the processes and the cycle times. Then we can calculate capacity based on this data on weekly basis, then on yearly basis. As we can see, process number 7 and process number 9 have highest cycle time, that is 17 minutes and 20 minutes. 20 minutes is the highest cycle time of engine testing, that is process number 9. It will define the production capacity of the whole line, about 9,000, that is 9,984, that is about 10,000 units with small adjustments. Same data is presented in the graphical form showing the annual production capacity. As you can see from this graph, the production processes are listed on the horizontal scale and the production volumes are listed on these bar charts. The last production process of engine testing has the lowest capacity and it shall define the line capacity of the whole system, and it is about 10,000 units. This is the process flow chart. This is on the same process sheets from the station number 1, that is washing, and passing through all these processes and the production line, passing through engine testing. It is delivered to final assembly line, that is frame assembly line. This is the situation before improvement. Now we want to debottleneck the processes, and that should be based on this principle. Suppose our cycle time is 16 seconds. If we add one more identical workstation with the same job contents, then our new effective cycle time will be reduced to half of the original cycle time. That is, new cycle time is 16 seconds divided by 2, that is 8 seconds. Our assumptions over here are the added workstation is exactly identical in capacity and efficiency. There are no additional delays like setup time, transportation, or coordination issues. Now, after completing this debottlenecking process, our situation is that our processes number 7 and number 9, that is differential assembly and engine testing. Now we have 2 workstations for each processes, and our cycle time is reduced effectively by half of the original cycle times. That is, differential assembly cycle time is now effective cycle times 8.5 seconds, and effective cycle times in case of engine testing is 10 minutes. This is the situation after debottlenecking. So if we compare the conditions before bottlenecking, the throughput time was 105.50 minutes. Now the throughput time is 87 minutes. And with the same working efficiency of 80%, the annual production capacity is now 17,000 units. It is based on the process number 8, which has the minimum capacity, and it shall define the line capacity of the whole system. The same is shown here in a graph, and the processes are listed at the horizontal scale, volumes are listed on the bar charts, and as I mentioned before, process number 8 is the debottleneck process, and it shall define the line capacity, which is 17,000 units per annum. Now we come to the action plans, recommended strategies and action plan to increase production volume. On the basis of short-term strategy, medium-term strategies, and long-term strategies. Our action plans for the short-term strategies are: number one, break down the job contents using time and motion study, line balancing, and Kaizen. It's a quick win, and at a minimum cost. Number two, staff training and development. This shall build foundation for improvements. Number three, overtime. This shall add capacity temporarily, shall increase labor cost, and make us fatigue. It is essentially not a sustainable long-term solution. Mid-term strategy. Add shifts. If the demand justifies, it shall potentially double output with the same machines. However, it needs increased supervision. Midterm number two, add complete production lines, new production lines. This shall increase capacity linearly, but if it required investment in space, equipment, and manpower, and is ideal for scaling if the market demand is sustainable. Lastly, long term, full automation. It is ideal for repetitive, high volume production, but it will involve high capital cost, may require complete redesign of layout and workforce rescaling. Reskilling. It's future proofing, especially for high volume production. This we conclude our today's presentations. Our next video discussion would be on frame or final assemblies of auto rickshaw. Thank you for watching. Thank you so much.